But we are here today to attend the talk by Professor Chi-ying Tsui, SRAM-based computing in memory design. So Professor Sérgio Bumpy is the session chair. So Bumpy will do the presentation of Professor Chi-ying. So thank you very much, Chi-ying, to accept our invitation. And thank you very much also, Sérgio Bumpy, to accept to be the session chair today.
So Professor Chi-ying Tsui is a full professor at the Hong Kong University of Science and Technology, and he's a distinguished speaker for today's seminar. He joined the department of that university, Hong Kong University of Science and Technology, in 1994. He's a full professor. He has achieved many awards and best papers and has a very prolific set of publications in IEEE. He holds 12 US patents. And he is currently the principal investigator and deputy director of two very important initiatives in Hong Kong, the AI Chip Center for Emerging Smart Systems, and also Innovation Hong Kong Research Center on this area. His research interests fall in the area of design and ICs and VLSI architectures for energy efficiency, embedded machine learning, low-power multimedia circuits and systems, wireless and artificial intelligence applications, and also power management circuits and techniques for portable devices. So with no further ado, we thank Professor Tsui for agreeing to deliver this talk for the Rio Grande do Sul chapter of CASS Circuits and Systems Society. The floor is yours, Professor Chi-ying Tsui.
So thank you for the introduction, Professor Bumpy. So today I'm going to talk about some of our works in related to the computing in memory design, particularly using SRAM. Before that, I want to take a few minutes to give you an introduction about HKUST. If some of you may not know much about us. So we are located in Hong Kong, which is Hong Kong is centered in Asia, and also Hong Kong is known to be one good city for students. We have 8 universities in a very small city, about 7 million populations, and so it's different from the normal impression from other people outside Hong Kong. So UST is not in the city center, so therefore we are enjoying a much better, so not so crowded environments compared with the normal city life in Hong Kong. So we are actually situated in the country park. So you can see the UST Stonehenge campus in this slide is probably one of the most beautiful campus in this region for them. And we are a young university. We established in 1991. We just finished celebrate our 30 years 2 years ago. And then so because we are focused on science and technologies, we don't have a large universities. We only have 5 schools, 23 departments, and a few academic institutes. And the number of students totally now we are reaching about 18,000, which is about like 55% are UG students, and then 45% are PG students. And our faculty size is around 750, and that's actually some of the figures about HKUST. And also I want to give you an idea on what the unit that this work is done is called ASSES, AI Chip Center for Emerging Smart System, which is centered actually supported by the Hong Kong government with about like $60 million for that. So the mission is to actually try to design AI hardware accelerators that actually can improving the performance or energy efficiency by 1,000 times, and also accelerating the AI chip design productivities and time to market. So it is an international consortium, not only by HKUST, but really mainly led by HKUST, but other universities, local universities, including Chinese University of Hong Kong, Hong Kong universities, Stanford, and EPFL, ETH, and also Notre Dame. So have faculty involving in this research centers for that. So we actually have a 4 research program that actually try to looking at the problems of how to design the next generation of AI hardware. So included the first RP research program is related to emerging technology for emerging computing system. Another research program is on architecture and heterogeneous system integrations. The third research program is related to UDA, how to use EDA to design AI hardware and also how to use AI in EDA. And the fourth program is on applications, how to build hardware accelerator for AI applications. And today's the presentation of work on SRAM design is mainly on our work in the research program too. So our center have like more than 30 faculty from different university. Here you can see actually we're faculty from HKUST, from Stanford, from Hong Kong U, from EPFL, from Notre Dame, and ETH Zurich, and also some individual faculty from all over the world for that. Okay, then next I'm going to talk about some of the work in SS that many particular looking at computation in memory. So this is outline of today's talk. So first I'll talk about the motivations, why we need computation in memory. Then we talk about the SRAM-based computing memory architectures that we are designing based on unique type of time-assisted current-based SIM architectures. So we're using this one in different type of networks, including convolutional neural networks, from binarized neural network to high precision macro design. And also that the same design can be used in also spiking neural network also. We talk about these three different applications of this time-assisted current-based SIM design. So without much discussion, I know everybody knows actually there's the importance of neural network, AI, application in the world. And nowadays, not only we're not talking about AI application in the cloud, but we are actually trying to move the AI application from the cloud to the edge. So one of the issues of deploying smartness or AI in the edge is one of the major issues is the energy efficiency, the power consumptions, and also the memory bandwidth, and all this. So in our centers, we have mainly focused on edge applications because for cloud, for server, so a lot of the space has been already occupied by big companies like Google, like other like NVIDIA's other big chip companies. So therefore, we are actually mainly focused on how to deploy or how to design energy efficient AI hardware accelerator for the edge computing. So as we said before, so one of the main part of using this deploy the smartness or AI in edge device is the energy efficiency. So we are working on some projects, the applications that related that we need to have a sensor that can have embedded smartness inside the sensor that can do different things, including object recognitions. For example, so this is one example that we're using, is actually using for head countings in certain rooms, certain occupants area for that. But at the same time, we want it to be very, very flexible. So we want the whole design to be powered by energy harvesting systems. So in that, so we need to design very, very energy efficient sensor that can actually do counting inside the device instead of sending back the data to the cloud or to the server to do the AI recognitions for that. So with that, so we also need to actually embed the whole network into the smart device. So therefore, we need to have a very good compression engine and also hardware friendly model for that. So therefore, the focus now is how to designing this low power CNN processor for this type of edge device. So traditional von Neumann architectures may not be suitable for actually increasing the energy efficiency because of the memory war that actually is well commonly known. So traditional von Neumann architectures, we have the process elements. So we need to fetch the data or instruction from the memory, either on chip or off chip, and then execute the process element for that. So for in AI applications, we have a lot of parameters we need to use for the computations, and using the von Neumann architectures that involve a huge amount of data movement between the memory and the process elements. So this is some numbers actually that quoted from a paper from Mark Horace for like a few years ago. So we can see that actually with the von Neumann architectures, the energies so mainly is spent on the movement of the data from the memory to the process element. So so depending on the size of the memory, so actually can be up to like a two order of magnitude bigger than operations that require in doing this for the convolutional neural network computations for that. For DRAM, it's even worse for that. So in order to solve this memory war issue, so so in this few years, one of the hottest proposal to tackle this memory war issue is try to do computing inside the memory. So that means actually embedding the computations into the memory for that. So with that, so we have the memory computing array, that inside the memory array, you actually embed some of the computing capability into that, especially so actually the multiply and accumulate operations for the CNN. So with that, we can actually do parallel operations inside the memory, and also without moving the data from memory to the processor elements. So we can actually save the energy for the data memory for that. And also at the same time, so because of the computations that actually specific use in the neural network computation, which is actually calculate the vectors to measure computations. So with that, so the memory computing array is actually can do highly parallel operation with that using mixed signal computations. So with that, so the energy efficiency will be increasing, and also by reducing the amount of intermediate data for accumulations, so that also that's contribute to the increase in the energy efficiency for that. So usually is the binary weights are actually stored in the memory array as the data, and also the activation is input in the either using a DAC or a driver to go into the memory computation array, and the column output is actually generate output for that. So there's different type of memory you can use for this computing in memory. So that including some emerging memory, which is mainly non-volatile memory. For example, the resistive RAM, the magnetic RAM, the ferro RAM. So all these are emerging memory that actually people suggest to use as for the CRM also. At the same time, we can use mature memory technologies, the mature technology, memory technologies like flash and volatile memory, like the SRAM for that. So while actually RRAM and MRAM are very promising because of their size and also the small size and also high density, but nowadays with the actual current technology for RRAM, the processor RRAM, that actually may not be easy to implement. So computing in memory with reliable calculations. So partly because of the technology of this type of RRAM is still need to improve. So one of the problems for example, RRAM is the variation issues. So RRAM, for example, so you actually can program the device into different resistance states, high resistance states and low resistance states. So from this curve, from the curve in the right side, you can see that. So even I program the current into low resistance and high resistance state, actually the conductance or the resistance of the device is not cannot be contributed very actually accurate. So you have variations in the conductance or resistance in the device. So you have the device to device variations. You also have cycle to cycle variations. And also one of the issue is the high write energy. So in order to write to the RRAM, so basically you need quite substantial energy for that. So with that, so if we need to do map calculations, that means multiply and add and accumulate the data together, and with the RRAM variations and process variations, if you need to actually accumulate many results, so then because of the variation, so you can have an overlap of the result, and then you will actually cause a quite significant error into the computations on that. At the same time, so now for modern CNN, you have very large capacities, and then so sometimes you cannot use a single SRAM macro to put all the parameters there. So sometimes you still need to actually update the memory quite often. So with that, the write energy become a bottleneck for for this deploying this SRAM into the real application, real deployment for that. So with that, so at the same time for non-volatile memory like flash, so the low endurance issue, the high wide energy issues, and all those not ideal effects that actually make it less attractive for that. So with that, so SRAM, so using the mature technology like SRAM is still one of the good choice for the at least for the this next few years implementations of the CIM engine for that. So with that, our so this project is focused on how to use SRAM to implement the computing memory for the computation for AI applications. So that. For SRAM-based CIM, you also have two types. We can actually do a digital CIM, and also we can do analog CIM. For digital CIM, so the data the weights are stored in the SRAM, and the input are actually going to the input driver to connect to the SRAM. And then, so basically, the weight is actually multiplied with the input, and then you have a digital circuits then do the accumulation, which is basically the adder trees. So there you have adder tree to add all this partial multiplication together. So therefore, the actual computation is embedded within SRAM cell today. And for analog cell, so basically is that you don't need extra adder cell. All this computation of the accumulation is by the summation of the current or summation of charge, and then using an analog to digital conversions to convert the analog signals, analog sum of all the accumulation into a digital signal for that. So these two actually approach have its advantage and disadvantage. So for digital CIM, so you have you have a very high precisions. You don't lose any precision because everything is done by digital. For analog, so you lose some of the precision because of the non-linearity, also with the noise. But then, so the area efficiency and also energy efficiency and also parallel computations is one of the advantage of analog CIM over digital CIM. So most of the time, so if for we design this CIM is for training purpose, so you need high precisions. So maybe digital CIM is more suitable. But for inference for small energy efficiency designed for AI inference that do not need very high precision, maybe 8-bit. So then analog CIM become is more suitable for that. So in this work, we're mainly looking at the analog CIM design. Okay, now first we'll talk about the first design that actually mainly using for binarized neural networks. That means the weights are either is a +1 or -1. Existing mixed signal SRAM-based CIM architecture is mainly based on two different mechanisms. One is called charge-based multiply and add accumulations. So basically, this is a cell for the charge-based MAC. So you have a SRAM cell, a 6 transistor SRAM cell, and +2, like a 2 branch of 2 transistor each together would form a 10 transistor cell here. So so this is basically is, so first we pre-charge the input. Actually the activation input depends on the multi-level pre-charge bit line. So we pre-charge bit line to multiple different voltage based on the value of the input activations. And then the multiplication with the weight is based on whether so the data in the SRAM will in the SRAM cell will turn on the branch of the bit line or bit line bar for that. And then depends on the sign if it actually will discharge the capacitor in this line. And after that, the accumulation part is based on the charge sharing of all these capacitors in the cell on these two lines, in the VP AVG and also VN AVGs. So this is actually the basic principle for this charge base. And then so after that, you need a linear search ADC to convert the analog value into digital. So another approach is current-based MAC. So in the right-hand side, so basically is the input activation is represented by multiple level of the voltage, using different voltage to represent the input activations. So if the multi-bit input, then you need a multi-level of voltage by using a digital to analog converter for that. And then based on the cell, and then so they will actually cause different size of the current flow through the discharge path for that. And then accumulation is based on the number of the amount total current that actually discharge for the bit line. And then so then you accumulate for the you pre-charge bit line first, and then the ultimate voltage, the difference between the pre-charge value and the final value is your accumulated value. Also, you need to have a voltage mode successful SAR ADC to actually convert the analog value in the bit line into digital value for that. So this both of these design need DAC for each input to convert your digital value into different voltage values, and also need to have ADC, separate ADC to convert the data into the analog data into digital data. So the main energy consumption of this kind of design is mainly on the ADC and also the DAC design for that. So in order to actually reduce the energies and increase energy efficiencies, so here we actually propose a new structure called time-assisted current-based MAC that utilizing some of the what we call discharge mode binary search ADC to do the AD conversions. So instead of actually the input is, instead of doing DAC convert the digital value into different voltage value into the as an input, so we actually convert it using a DTC to change the and to convert the digital input value into time, into different time modulating pulse, and then we use a fixed current to actually to discharge it. So therefore, the accumulation, the multiplication is depends on the time, the total time that you discharge the bit line, and accumulation is on the bit line and bit line path as the voltage drop, voltage discharge by the each bit cell for that. So also in this design, we actually propose new way to do the ADC without actually dedicated ADC to do that. We use a bit line and bit line bar to do what we call discharge mode binary ADC that we are going to talk about it more later. So overall, so architecture will be like this. So this is the like array, for example, is a 64 by 64 10D SRAM array. So the 10D SRAM is basically each cell consists of 160 RM cell, 60 SRAM cell, and then two different branch of discharge. Each branch consists of two transistors there. And then this also we have the digital and to analog conversion is done by the digital to time converter and a multiplexing trees that actually, and also a driver that actually deliver the pulse, the time pulse into each word line of the array for that. And then for the AD conversion, so we're using a discharge-based ADC. So in the right-hand side, you can see that actually the upper part is the SRAM array. The lower part is actually the discharge ADC type. So after we finish accumulations, then we go through the ADC process. In the ADC process, we compare the two bit line, the bit line bar and bit line. So then depend on which one is larger, then the one that's larger will be actually using modulated pulse to discharge. That depends on the resolutions of the ADC conversion for that. So this is what we call discharge-based ADC. So the mechanism is like this. So the embedded ADC based on this DAC-based mechanism is like this. So the formula here is actually, we can see that because the weight is either +1 or -1, and then when it's +1, we discharge the bit line. When the weight is -1, we discharge the bit line bar. So therefore, we have these two values, which is the voltage value in the bit line and bit line bar after at the end of the MAC mechanisms. We can see that the difference between the two bit line bar is actually equal to the summation of the input value activation times the weight. So then now we go through a binary search process. We compare the bit line bar, and then if the bit, for example, this example, if the bit line bar is larger than bit line, then the first thing is actually you discharge the bit line bar using using the delta V that is related to the resolution that we have right now. And then we go through the process one by one, and then every time we compare the bit line bar voltage and the bit line voltage, and it depends on which is larger, we actually discharge that with the delta V at that bit resolution for that. We can see that actually each bit minimum resolution is the smallest pulse times the actual current times for that. So therefore, depending on which bit resolution we are doing right now, then we actually apply the right number of pulse into that to discharge that bit line. So with that, that basically that and the right hand side you can see that actually either depending on which path I want to discharge, and then the correct modulating pulse will apply to the corresponding discharge path to discharge the bit line and bit line bar. So until at the end, both the voltage are the same, then we finish the ADC. So by doing so there's a few advantages of doing that. So first, using the time-based approach, so we achieve a good linearities throughout the MAC and the AD operation. We use the same mechanism to do the MAC and also the AD, and then we can show good computational linearity. So the right-hand side is actually the measurement result that we have from the array with a matrix vector multiplications. We can show good linearity, and also we actually measure the computation accuracy. So we can see that most of the time, when we accumulate different data here, the measured data and the field data, they're only maybe off by like at most 0.2% for that. And also the energy efficiency of the discharge ADC is much better than the traditional SAR ADC, because now we only need to charge the bit line once. During the ADC, we don't need extra charging of extra capacitor array. We only discharge the bit line bar, which is you only need to charge once for the MAC operations on that. So with that, we can actually achieve a very actually efficient AD conversion for that. At the same time, so the only additional hardware you need is basically some comparators. So we can actually achieve parallel operation by having a comparator for each column from that. So to make a comparison of the traditional SAR ADC and our discharge-based ADC, so we actually compare with one actually SAR ADC reported in the JSSC. So we try to compare with a similar number of ENOP and also SNDR. So they can see that actually the area is much smaller, the power is smaller, and also the number of the energy that actually per conversions for like a conversion is also like a few times smaller for that. So we fabricate the chips in like 65 nanometers, and then we actually do the measurements in here, and then we compare with some of the existing approach for that, so we can actually achieve a very good we can achieve the highest output bit width, so about 11 bit for output bit, and also achieve very good energy efficiency and also FOM compared with other design. And also we're looking at the accuracy by using this design, see whether it actually will cause any degradations. So we use Net5 network for MNIST data set. So the baseline software accuracy for like a 4-bit input binary neural networks, the accuracy is 70. The loss in accuracy is only 0.01%, which is very negligible. So next, we're looking at actually another design, how to expand this design into like doing high precision, multi-bit high precision applications for that. So for modern CNN applications, so we want to have a higher accuracy or larger data set, then we actually need to have a higher output precision for that. So, but with high precision, so the complexity will be higher, and also the energy will be higher for that. So now for existing approach for using SRAM-based CIM to achieve high precision, so actually have fall into two different categories. The first category is because we don't want to have use a very high precision ADC because the energy consumption will be very high. So some of the works are using actually a low precision MAC, but we actually limit the accumulations of the weight into a small number so you won't actually lose much the accuracy using low bit ADC. But then we want to achieve a high output. So basically, we actually for each sections we do a low bit and then we do a digital shift and add together to get a high precision output for that. So with that, we can achieve a high output, but the throughput will be lower because now you cannot accumulate all the data together. You need to separate into multiple sections. You need to use multiple cycles to accumulate data together. So therefore, the speed will be lower. At the same time, the energy efficiency will be lower because you need to use multiple amount of ADC conversion. Your number of ADC conversion will be higher for that. So then you sacrifice the energy efficiency and parallelism, but you act for getting a better accuracy for that. So another way to do that is actually you use a relatively high number of ADC. So basically, so you actually now every unit you don't do the whole number of rows for the array to do so accumulation. Instead, you accumulate each section using a separate capacitors. So therefore, so the accumulation will be smaller. But then after that, you're actually using a charge sharing to actually accumulate the multiple section of the capacitor together. So with that, so we can do all the computation or accumulations in parallel. So the speed will be good. The energies, however, energy efficiency depends on the number of bit of ADC you're doing. So if you're actually looking for like a better energy efficiency, you cannot do high number of ADC. But at the same time, so then the accuracy will lose. You will lose the accuracy because actually, so the ADC output resolution is not high. So with that, we want to actually achieve both a good energy efficiency, a high accuracy, and also parallelisms. So therefore, we actually propose to extend our like a time-based MAC for the binary neural network to actually support multiple bit weight for that. So instead, so now this is the actually architectures that can support multiple bit weight, multi-bit weight using the TAC-based mechanism for that. So now, so this design actually looking at if we are using a 4-bit weight, okay, and also a 4-bit input. So we have a 4 analog Simon core, and each one have a 4K bit SRAM cell organized into 64 by 64, and then each column of the RAM, 4 column of the RAM will actually merge together into one weight with a 4-bit there. Okay, yeah. So now we're using the time assisted base. That means actually the pulse is using pulse to represent the input activations, and also you can also use the discharge based ADC to do the calculations. Now all this 4 column will actually use to discharge 1 bit 9 and bit bar represent the data of the accumulations of the 4-bit activation multiplied by 4-bit weight for that. But in order to actually make it more efficient and more faster, so the cell we are using is actually modified from a little bit from the original 10T cell that used in the binary neural network. So here is actually the cell we are using is a 9T differential SRAM cell design. So basically, it consists of 2 types. So because it's actually signed weight, so we use a sign magnitude representations to represent the weight. So the bit 3 is actually the weight, and bits 2, bit 0, bit 1, bit 0 are the actually magnitude of the weight for that. For the magnitude weight, basically the cell is like this. We have a 6T SRAM cell that control a discharge transistors, and also we have 2 transistors here that actually one is connected with bit 9, one is connected with bit 9 bar. It depends on the sign of computations. If the partial product is a minus, is a negative value, it actually turn on the connection to the read line and then discharge read line bar. If the magnitude is positive, it will turn on the transistor connect the read line to discharge read line for that. So therefore, depends on the value of the 1 bit of the products of the activation and wait, either read line and read line bar will be discharged. Now, actually, one of the things we actually modify from the 20 cell is that the input is no longer actually connected to the transistor in the word line, but instead the pulse, the input pulse is applied on the source node of the transistor M0. The reason of that is actually the capacitor will be smaller, and then so therefore the overall driving of the pulse will be smaller, and then the energy efficiency higher, and also slew rate can be actually get better for that. So that we actually reduce the noise at the input for that. And then so the data store in the sign bit, actually the cell is not used to actually discharge because the sign bit doesn't depends on the values of that. So the sign bit cell, actually later we can use it for the ADC purpose. In the ADC purpose, we can use the sign bit to actually for doing the discharge of the data to do the discharge for ADC. So altogether, the overflow is like this. Yeah, so this is the one row that we have actually the sign bit here, and also the 3 bit represent the 4, 2, and 1 magnitude on that. And then so now the pulse get into the each bit, it depends on the weight of the location of weight, also times the activation, and times the delta t. Delta t is the minimal time represent the minimal resolution for that. Yeah, then depends on the sign that actually we are going to discharge the read line and read line bar. So by multiply, so therefore the multiplication of the value of the 3-bit activation and the 3-bit weight, then actually depends on that. Then we will discharge the read line and read line bar. So now the activations is also represented by sign magnitude format for that. So with that, so then later we'll see why we actually want to represent it as a sign magnitude format, because you can actually increase the noise margin and also can reduce the time to do the discharge for that. So altogether, this is the flow. So we go through the time diagram. The first, we do the MAC operations. So we have 4-bit input. So each bit depends on the values. We're actually sending the pulse into the corresponding pulse into the different bit locations, and depends on the value. Actually the width of the pulse is actually given by the table here. So it depends on whether it's in the least significant bit on also the bit 2, and depends on activation value. So if the activation bit is a 0, so the pulse width is 4 delta t, 2 delta t, 1 delta t, and then actually on the third activation bit is 16 delta t, 8 delta t, and 4 delta t for that. So after four actually triggering cycle of entering the activations, then we go through the ADC process. First, we compare the read line bar, and then so it depends on the value. So you determine the sign, and then after that, for each AD operations, then we actually we apply the corresponding pulse width into the sign, actually the source string of the sign, the source node of the sign bit delta, which is used for discharge. The bit line and read line bar depends on the value of the comparator output for that. So here we're actually looking at a 9-bit resolution after 9 cycles, so we can get the data out for that. So with that, so this is the overall MAC and DAC flow. So basically the MAC, the multiply and accumulation cycle, and also the analog digital cycle flow is the same. So they're using the same data flow and also the same cell to do that. So therefore, you can generate a very actually good linearity, and also that actually you're just using again the discharge-based mechanisms. We don't need other ADC approach. We just actually doing the comparison of the bit line bar and discharge it and get the value for that. Now, one way actually we want to improve the precision accuracy. So therefore, we want to enhance the signal margins. So signal margin is basically like this. So now it depends on the number of bits you want to do. So therefore, the MAC step is basically the VPP represent the voltage headroom. That means actually the voltage, the difference at the bit line from the maximum to minimum for that. And then when we divide the voltage headroom with the actual total number of value of MAC steps, this is the MAC step. And then so if by looking at that, so but each values of the adjacent value, so we have some like variations there. If the variations so actually is larger, your signal margin will be smaller, and then your error is larger. Okay, so in order to enhance the signal margin so that you have a higher accuracy, we can do two things. One thing is actually we want to have a larger MAC step size. So that means if the MAC step size larger, the difference between the two adjacent values in the MAC value is larger. And the second is actually we try to suppress the noise of the distributions. Now, in order to make the large MAC, the MAC step, so one of the way we can do is that actually we can reduce the dynamic range of the actual values for that. So we can use, if the summation of MAC value is smaller, then by using a fixed VPP headroom, so basically your step size will be larger. And then so you will have a better signal margin for that. So one of the way we're doing the actually increasing signal margin by reducing the dynamic range of the calculation is that we're using sign magnitude representation for the activations. In fact, most of the actually CNN operations, so activation is after the release. After release, usually you remove all the negative values, so you only have positive activations. So if examples, if you have a positive activations, we actually have a 4-bit, so that the range should become from 0 to 15. And if we multiply the weight by -7 to 7, so your total range is from -105 to 105 for that, which is actually, so even you use some sign magnitudes, that means the magnitude you need to have a 105, so a step to represent the whole data for that. But now if actually we do a shifting first, we subtract the activation by a constant. For example, we subtract the activation by 8, then the activations, the representation is now -8 to 7. When you multiply -8 to 7 with -7 and to 7 of the weight, so your dynamic range is from -56 to 36. You only need to represent the absolute value, which is 56. So compared with the original, so dynamic range, which is 105, so we reduce actually the step size, the dynamic range by almost half, so that you can achieve to have a larger step size. Now, with that, the calculation is that, so we actually subtract the actual activations by a constant 8. And then, but because the weights are all unknown before, this subtraction will actually result in just a constant shift from the actual output values. So therefore, after the calculations, we can add back this offset to the digital output of the AD process, and then you will get back the actual value for that. So this is actually this add back and then subtract is very low cost for that. But with that, we can enhance the MAC step by almost half. Then we can actually achieve a better signal margins. At the same time, so for a lot of this data and activation on the CNNs, so after that, so activation is actually the distribution is shown here. So a lot of times the activation value is small, it's close to 0, it's a small value. But however, when we actually were using the time pulse to represent a small value, usually your error, your actual relative error is large, because actually when the pulse is smaller, so you have an edge, the noise value, the edge will be relatively larger. So therefore, the noise will be larger if your activation is smaller. But by actually shifting the value from a small value by subtracting 8, now you're moving the value from a very small magnitude actually to most of the time it's a large negative value for that. So with that, your noise effect is also smaller also. So with all these two actual signal management margin enhancement technique, so the error can be actually become smaller for that. So altogether, when we try to compare our approach with that two approach that we talk about, the charge-based approach, so the actual multiple section using digital accumulations and also using this charge sharing approach, so we can achieve a smaller number of digital accumulations, and also we can achieve a smaller ADC energy, and also enjoy a higher accuracy for that. So we implement this chip in 40 nanometers, and then we actually test it with different convolutional networks. So here we're using a Cyber-10 example to show that. So this is measure energy and different input sparsities. So it depends on the sparsity, input sparsities. You can see that actually the energy is decreasing. It's actually increasing with the sparsity. So the energy efficiency is decreasing, but it's actually can achieve a really good energy efficiency for different sparsities also. So this is a comparison with the state of the art. So we can we achieve a very, very good comparison with energy efficiency. It's higher, and also depending on whether we do a 4-bit weight or 8-bit weight. So we can actually get the highest FOM comparison for that. So this is the chip summary. So on that, so this is we're also actually looking at the accuracy, so impact on using this approach compared with a software approach. We can see that actually we can achieve for Cyber-10 a 91.6% accuracy compared with a baseline software accuracy of 92.1% for it. So I need to. Now the last work we want to look at is actually is on using this cell design and macro design for spiking neural networks. Here we describe one of the applications is on some edge healthcare system for that. So usually, so for edge healthcare system, we have a sensor that actually doing the biosignal acquisitions and convert the analog signal in digital signal, and then going to the AI processor to do some classifications and then output it. So for this, if we want to use an edge healthcare system, that means actually we want to have a device that has a wearable device for these detections. So we want it to be very, very low power for that. So there's some challenge for this scenario. One is actually you always need to actually sample the data for processing. And a lot of times, so for example, we're looking at one example application is the ECG detections. So then a lot of times after the samplings, a lot of data is very small and close to zero. And then you have a lot of redundant data there. At the same time, you also have the memory wall for the computation if we want to use like a traditional way to do, like a digital way to do this computations and that. So in order to solve this issue, so we actually proposing a sensor-defined system that actually consists of a few different things. So we actually convert it into a spiking neural networks. So first, we actually design a sensor that is not using traditional just ADC to sample the data, but instead you will actually convert the data, analog data, directly into spike, and then the spike we send to the neural processor, and then generate different pulses spike into the computation engine. And we use SRAM-based computation engines to implement a neuron in memory processor. With that, so we can actually reduce the amount of data that we need to send, and also we actually doing the SNN computation in the analog domain for that. So with that, we can actually save the amount of data by about 50% to 90% on that. And then using SRAM-based in-memory architectures, we can overcome the memory wall. Now let's looking at the actually detail of the design. So the architecture is like this. First, we actually have a two-chip solution. The first chip is actually a sensor chip. It's a level crossing analog to spike converter chips So instead of actually sample data using ADC to convert the value into value, we actually compare the inputs, the capture signal with a level, with some voltage level, and then if it cross a level, we generate one out, a spike out for that. And then the spike we will collect and we send it to these power chips that based on the spike pulse, and then the internal there's a pulse generator based on the spike train. Then the actual different pulse width will be sent into the power core. The power core is basically the SRAM-based computation engine, and then do the computation. So mainly we are doing like an integrate and fire type of spiking neural networks. So this is actually a little bit more details on that. So our event-driven sampling, basically you compare with different level. It's across the level, we generate a pulse. Then we have actually something called up pulse and down pulse. If actually when we actually have compare with the certain levels, when we larger than this level, and then the trend is going up, you will generate a pulse in the up. And then when you're going down, we generate pulse in down. And then we code this pulse into a sequence of 1 or 0 in the up pulse, in the up spike stream, and then the down spike stream for that. And then we merge these two streams and then send it to the processor to the spiking neural network that implement the power chips for that. So the training is basically we use this like a stream to actually do the training for this spiking neural network. Now, this is actually a power core that we are looking at how to implement the actual integrated and fire circuits. So basically, we are looking at a 3-bit weight. So it's a silent weight also. So we actually have using 64 byte and 64 array of the SRAM. We divided into like a 16 bank. Each bank have 4 active cell weight to represent a 4-bit cell for that. So it's also assigned representations. So it depends on the input pulse. If there's a pulse coming in, it's a spike coming in, actually the pulse generator will generate different width of the pulse. 4T is going to the second bit. The 1T is going to LSB. So therefore, they will actually generate the accumulated current with different pulse together to discharge the corresponding bit line and bit line bar for that. So this is the integration part that actually integrates the neural spikes with the weight together. But at the same time, we need to actually implement the integrate and fire part for that. And then we need to actually compare the values of the neuron compared with threshold. How do we implement the threshold? Because the threshold will be different and different layer for that. So the threshold is also actually doing the same thing in the memory bank. So we divide the memory bank into 2 parts. One is actually for the actual spiking neuron. The other is for the threshold generations. The threshold generations, the threshold value will be actually decode and represent into a pulse also. And the pulse will actually, for the threshold calculations, the pulse will discharge the threshold bit line in this bank for that. So when we compare the positive bit line and the negative bit line, it's basically we're comparing the absolute values of the integration and also the threshold together with that. So then whenever the bit line plus is actually less than the threshold bit line, then we know that actually the integrate value is larger than the threshold, and then we fire it, and then the output pulse will be generated. So altogether, so this is the idea. So basically, so the cell can, so the same type of cell. So some of the cell will be used for the integration path. Some of the cell will be used in the threshold path. We can actually using it to configure different role of the cell can be used in as the threshold calculation, and different role can be used in the integration application for that. And this is the timing diagram. So basically, whenever there's a triggering signal, the pulse will be going into each row of the So the corresponding neuron input will be going into the integration path. The threshold configuration signal will be going to the threshold generation path. And after that, so we compare the bit line and also the threshold line. And then so it depends on the value, so whether you actually fire the output or not. So this is a more like a detail of the spiking data flow for one bank. So this is the input spike with the 1 or 0. So actually data coming from the sensor, and then that together with the pulse generator, this is handshaking. It will generate different pulse signal and going into the configuration cell, and either is using as a integration cell or the threshold cell for that. After that, we compare the bit line and the threshold line, and then if the accumulation line is actually smaller than the threshold line, then the integration, the comparator will generate a pulse out, will generate a fire of the output spike out, and then going to the next stage for that. So we also implement all this in 40 nanometers. So this is a chip that's the testing that we have. So this actually, you can see that so the different parameters, we support 4-bit weight, and then the throughput we can achieve like a very, very high throughput and also very low energy per spiking operations on that. So we using this chip to actually divide it on an ECG-based arrhythmia detection. So using the MIT BIH data set for that. So we map. So this actually spiking network have 5-layer actually is a spiking network. So 2 layer of convolutional integration fire, 1 layer of maximum pooling, and 2 layer of fully connected IAF. Then we map all this network into this neuron in memory computing chip for that. So this is comparison with the sum of the art. So actually we achieved the lowest energy, the highest energy efficiency per ECG task. And then so when we compare with all the analog implementations, we have actually the highest accuracy and also the best energy efficiency for that. So for digital ones, they actually can achieve very high accuracy because actually they can use many higher bit width for that. But the energy efficiency, so that's lower than the analog based computations of that. So with that, actually, and then we concluded talk. So I gave one of the design that we are doing is actually based on this time assisted current based SRAM approach. We can utilize it in binary network, or actually we extend it to support multi-bit high precision, so CNN computation. At the same time, you can actually configure it to remodel it as to use in the spiking neural network applications for that. So this concludes my talk. Thank you.
Okay, thank you, Professor Tsui. It's a very interesting set of work in computing in memory. I have a question regarding the 2 last architectures. The applicability of the technique with respect to the number of bits of the weights. You have used sign magnitude in the previous one, and then also a different set of approach for the spiking. When you have more than 4 bits weight, how applicable, for instance, would be the
if we
the
actually
90,
for
second chip architecture?
Yeah, it's a good question. So for 4-bit, for example, if I want to do high precisions, then we use 2 column. Actually, that means we are using like a 2 accumulation, and then we shift and add together to achieve that. So we can do this. Because if we extend it to 8-bit within the pulse, that 10 pulse will be maybe too long. So we want to keep the pulse not to be so long. Then actually, so we need to actually combine like a we want to support high bit width. Then you can sacrifice some of the energy. So you need to do actual shift and add together. So that means the first 4-bit and second 4-bit, they actually separate between the ADC and then ship and aggregate.
Okay. And when you do the let's say the digital to time conversion for the pulse width modulation for 1 delta T, 2 delta T, how you calibrate what's exactly delta T, and can you give some more consideration
Actually,
to the
so
circuit,
we have in the paper
for the
we
second
have
example?
Yeah, in the paper we actually describe circuit is actually an sockets that actually you can actually do calibration on the chip to actually adjust the bit width so that you can to accommodate for the variations on the chip for that. So we have some calibration circuits before you use it, you can calibrate for that part for that. Yeah, so we can refer to the detailed circuit design in the paper.
Okay.
So it's
Great.
basically it's
Well,
actually
for you in the
yeah.
Excuse me, can you repeat?
It's basically
Basically?
actually a ramping circuits that you can actually tune the current to generate that. The different
Okay.
actually small variations of calibrations on that.
Right. Well, it's a very interesting set of works, actually, 3 very complex circuits with very innovative ideas. The audience here, thank you very much for your very interesting talk, Professor Tsui. And with no other questions being addressed by the audience, it's only up to you to, let's say, to do your closing remarks, and then we will close the session soon. Can you tell your last remarks? Because basically we're seeing here a high level of energy efficiency of hundreds of terawatts per watt, and those are really groundbreaking. So
Actually, so
your
we
last
have
words, Professor Tsui.
yeah, I think actually CIM is very promising. Actually, we have different group in our centers looking at different type of CIM design. So we have a group working on digital CIM, SRAM-based. We also have a group working on RM-based CIM. So of course, so we actually we're looking at some way to actually how can we accommodate the variations of the RM. So of course, RM will achieve a very high energy efficiency, but all the problem is about the accuracies. So how do we use to pick the right CIM to use? So basically, it all depends on the type of applications. So we need to target. So we have different trade-off in terms of accuracy, in terms of throughput, in terms of energy efficiencies, and that. So that's actually there's still a lot of work we can actually work on these issues.
Okay, thank you, Professor. So with that, we conclude this CASS talks of this series promoted by the Rio Grande do Sul chapter. And with no further ado, I'll get the word back to Ricardo to close the session. Thank you very much, Professor.
There is a
Chi-ying Tsui.
There's a question here. There's a question here.
A question by Talha Bil Aslam from India.
Yeah, actually, so the shift and app block for multiple, so we increase area, is compression presented with weighted. Actually, so So if for our design for 4-bit weight, 4-bit input, we don't need to have a separate shift and add block. Only when we do 8-bit weight. So that actual compression is also with the weighted multi-bit precisions already.
Okay, so thank you very much, Professor Chi-ying, for this very, very nice, interesting talk. Thank you, Bumpy, for sharing the session today.